Hi children, welcome to another chemistry class. In this session, we are discussing the chapter alcohol, phenol, ethers. Alcohol, phenol, ethers, right? All of you know what is meant by alcohol. Alcohols, the general formula is ROH. It is hydroxy derivative. Alcohols are hydroxy derivative of aliphatic compounds, right? What about phenol? Phenol is hydroxy derivative of benzene, isn't it? Hydroxy derivative of benzene, that is phenol. Pinna, ethers. Ethers are ROR. Symmetric ether, ROR dash. Unsymmetric ether. This is called a symmetric ether. And this is called unsymmetric ether. So symmetric ether and unsymmetric ether, so called simple ethers and mixed ethers, right? Ethers will have a functional group divalent oxygen, and alcohols will be hydroxy derivative. They can also be treated as derivative of water. You see the water molecule HOH. Replacing one of the hydrogen atom with the alkyl or aryl group, you get alcohol or phenol respectively. When both the groups are replaced, you get ether, isn't it? So this is alcohol and this is phenol, right? And that is ether. Ether is of two types. And simplest alcohol, all of you know, methanol, CH3OH, simplest alcohol, the so-called wood spirit. And then ethanol, CH3, CH2OH, the so-called fruit spirit or grain spirit. Ethanol, the most wanted mother liquor for the biggest industry in the world, right? This is poisonous in nature. Methanol is toxic in nature, while ethanol is the mother liquor used in beverages, drinks, and finding many industrial applications. While this is phenol, and simplest ether will be dimethyl ether, CH3OCH3, dimethyl ether. And there is aromatic ether also. Aromatic ether also. This is aromatic ether, the so-called methoxybenzene, anisole, the very famous anisole, methoxybenzene, aromatic, simplest aromatic ether, right? That is about the functional details of alcohols, phenol and ether. Alcohols will have ROH group, and to be precisely it can be drawn like this, ROH, like this, right? Fine. When you look at the classification of alcohol, there can be monohydric, dihydric, trihydric. There can be one OH group like this. There is one OH group like this. All of you know this is ethanol, ethyl alcohol. It can be two OH group like this. What is the name of this molecule? Ethylene glycol. This is called glycol, ethylene glycol. It can be three OH group like this. What is the name of that molecule? Exactly. Glycerin or glycerol. Glycerol or glycerin, trihydroxy. So it can be monohydroxy, it can be dihydroxy, it can be trihydroxy, right? Is this a vicinal or geminal? Is this vicinal or geminal? This is vicinal diol. This is vicinal triol. What about geminal diol? What about geminal diol? CH3, CH, OH, OH. This is gem diol. Hardly you find a gem diol. Hardly you find a gem diol. Why? Gem dihalide is stable, but gem diol is unstable. Immediately there will be losing of water molecule and it will turn aldehyde. That is the issue. So gem diol is not that much stable. Gem vicinal vis diol is stable. Gem diol is not so stable. So alcohols may be categorized like that: monohydric alcohol, dihydric alcohol, polyhydric alcohol. All of you know carbohydrates are polyhydroxy compounds. right? And there is further classification. All of you know primary, secondary, tertiary alcohol. Primary, secondary, tertiary alcohol. What is the mode of classification? That too is known to all. Primary, secondary, tertiary alcohol. RCH2OH. This is a primary alcohol. The OH group connected to primary carbon. Or it is RCHROH. This is a secondary alcohol, that is R2CHOH. This is a secondary carbon atom, or it can be RCRROH. This is a tertiary alcohol. So accordingly, where the OH group is connected to, is it connected to primary carbon, secondary carbon, or tertiary carbon? You can call it as primary alcohol, secondary alcohol, tertiary alcohol. This is a primary alcohol, this is a secondary alcohol, and this is a tertiary alcohol. So monohydric, dihydric, polyhydric, that is one categorization. Primary, secondary, tertiary, that is another categorization, right? Let's have a look at the next categorization. Allyl alcohol. See, the alcohol group connected to allylic carbon. This is what called allylic carbon. All of you may be aware of. This carbon is called allylic carbon. What is an allylic carbon? An sp3 carbon linked to an alkene unit. This is an alkene unit to which a carbon, sp3 carbon connected. That carbon is called allyl carbon, and the OH group connected to that carbon is called allyl alcohol. This is allyl alcohol. How comes the UPSC name of allyl alcohol? And also understand, allyl alcohol can be three types. This is primary allyl alcohol, while this is a secondary allyl alcohol. You see the alkene group, and this is allyl carbon, but that carbon is connected to, you see that, secondary, CHOH. This is CH2OH primary, CHOH secondary, and COH tertiary. So allyl alcohol can be of three types. Primary allylic, secondary allylic, and tertiary allylic. Primary allylic, secondary allylic, and tertiary allylic. Is it clear? Fine. Now, what is the UPSC name of this molecule? This is simply called allyl alcohol. This is simply called allyl alcohol. What is the UPSC name? It is 1, 2, 3. It is proper 2-in-1-all. Proper 2-in-1-all. That is the UPSC name of the molecule. So, categorization number 1 based on the number of OH group. Categorization number 2 based on the nature of the carbon atom to which OH group is connected, that is primary, secondary, tertiary. And the third one, allyl alcohol. Adil thanne primary, secondary, tertiary. Primary allylic, secondary allylic, tertiary allylic, like that. Next is benzyl alcohol. How comes benzyl alcohol? This carbon is called a benzylic carbon. This carbon is called a benzylic carbon. The carbon connected to benzene ring is called a benzylic carbon, where OH group is available. That is benzyl alcohol. Benzyl alcohol again can be primary, CH2OH, secondary, this is primary, CH2OH, secondary, CHOH, secondary, and tertiary, COH, tertiary. Benzylic alcohol, right? How comes the UPSC name of this benzyl alcohol? What is the systematic name of benzyl alcohol? Name is enough. The name benzyl alcohol is enough. Benzyl alcohol. That name is enough. But again, what is the systematic name? It may be called as phenyl methanol. Phenyl methanol, like that. Okay. Now there is another category, vinyl alcohol. This is called vinyl alcohol. Vinylic alcohol. But remember, vinyl alcohol may not be stabilizing much because of a phenomenon like this. You see, this hydrogen will migrate to this carbon. CH2 carbon will become CH3 carbon, and CH carbon oxygen will carry a double bond. You get a CHO. Vinyl alcohol will turn ethanol. What is the kind of isomerism known as? What it is called? Isomerism called a very popular one, tautomerism. So a vinyl alcohol may tautomerize. A vinyl alcohol may tautomerize, giving aldehyde ketones like that. Okay. Now coming back to here, we have again phenol content, monohydric, simply phenol, hydroxybenzene. Again it is monohydric. Methyl phenols are called cresols. Methyl phenols are called cresols. How many cresols are available? How many cresols are available? 3 cresols. Orthocresol, metacresol, paracresol. This is orthocresol. When the CH3 group comes here, metacresol. When it is coming here, paracresol. Right? Yes. This is dihydric alcohol, catechol, dihydric alcohol, catechol. This is trihydric alcohol, trihydric alcohol, right? Yes. And coming to ethers, already I have commented simple ether, symmetrical ether, or mixed ether, unsymmetric ether. Simple ether, mixed ether. This is a simple ether, ROR, simple ether, symmetric ether. ROR dash, that is a mixed ether. So two different alkyl group when comes, it is mixed ether or unsymmetric ether. When same alkyl group is coming or same hydrocarbon group is coming, it is called a simple ether or symmetric ether. So ROR, simple, symmetrical, ROR dash, unsymmetrical or mixed ether, right? Yes. Try to go through the IUPAC name and all for the given molecules. And they are asking, so try to figure out all these possible ones. For example, asking what is the kind of this molecule? Is it primary, secondary, tertiary? Is it primary, secondary, tertiary? We can simply understand it is CHOH and it is secondary in nature. CHOH, it is secondary in nature. Right? And what will be the IUPAC name? IUPAC name will be 1, 2, 3. 1-phenyl propan 2-ol. 1-phenyl, 1-phenyl propan 2-ol. Like that. Right? So try to figure out such exercises given in the textbook. Right? Only when you practice, there will be doubts, which definitely can be discussed in detail in the classes. Asking how many are allylic alcohol? Is it allylic or not? Is this, for example, is this allylic or not? Yes, it is allylic. Double bond is there and this carbon is allylic carbon and this is allylic alcohol. What allylic? Primary, secondary or tertiary? It is a tertiary allylic, COH. Allylic at the same time tertiary allylic, like that. So try to figure out all such examples in text questions given, also the molecules given like this and their naming: methanol, N-propyl alcohol, isopropyl alcohol, N-butyl alcohol, secondary butyl alcohol, isobutyl alcohol. This group is called isobutyl group. This group is called isobutyl group, while such a connectivity called secondary. While such a connectivity called N-butyl, N-butyl, secondary butyl, isobutyl, while this is tertiary butyl, tertiary butyl. Ethylene glycol, already seen. Glycerin, already seen. Glycerol, glycerin. Propane, 1, 2, 3 triol, glycerin or glycerol. Propane, 1, 2, 3 triol. Cyclohexanol, 2-methyl cyclopentanol. Phenols, phenol, cresol, orthocresol, orthocresol, metacresol, paracresol. What is IUPAC name? 1, 2, 3, 4. 4-methyl-phenol. This is 3-methyl-phenol. This is 2-methyl-phenol. So on. And this is dihydric catechol, resorcinol, quinol. 1,2-dihydroxy catechol. Benzene 1,2,3-diol. 1,2-dihydroxy, that is catechol. 1,3 called resorcinol. 1,4 very popular quinol. And there is trihydroxy, popular trihydroxy compounds, very popular trihydroxy compounds. 1, 2, 3. 1, 2, 3 trihydroxy, very popular. Pyrogalol. 1, 2, 3 trihydroxy, pyrogalol. Or there is symmetrical one. 1, 3, 5 trihydroxy, fluoroglucinol. 1, 3, 5 trihydroxy, symmetrical one. 1, 3, 5 trihydroxy, fluoroglucinol. This is pyrogalol. 1, 2, 3 trihydroxy. Among dihydroxy, the popular one are catechol, resorcinol, quinol. Among trihydroxy, very popular two molecules, pyrogalol, fluoroglucinol, etc. Right? Fine. And some common ethers. Dimethyl ether called the methoxy. Ethers will be named as alkoxyalkane. Ethers will be named as alkoxyalkane. Alkoxyalkane. This is simpler alkyl group and this is bigger alkyl group. Alkoxyalkane. You see that methoxypropane. 1 methoxypropane. It is 1, 2, 3. 1 methoxypropane. Like that. This is the very popular one, anisole. Anisole itself is a UPSC accepted name and is systematic name methoxybenzene. While ethoxybenzene called phenetol. Methoxybenzene called anisole. Ethoxybenzene called phenetol. Ethoxybenzene. Heptyl phenyl ether. 1 phenoxyheptane. 1 phenoxyheptane. There can be multiple alkoxy group. You see methoxy. So it is 1, 2 dimethoxyethane. There can be more than one alkoxy group. 1, 2 dimethoxyethane. It is named after this ethane. 1 methoxy, 2 methoxy. 1, 2 dimethoxyethane. How to name this molecule? Is it 1, 2 or 1, 2? It is 1, 2. 2 methoxy. Sorry, it is ethoxy. 2 ethoxy. 1, 1 dimethyl cyclohexane. Lowest locant rule. In fact, alkoxy group doesn't get any privilege in numbering. Only alphabetical privilege, that's all. Lowest locant should be taken into consideration. So it is 1 here, 2 here. 2 ethoxy. Naming will be in the alphabetical order. 2 ethoxy, 1, 1 dimethyl cyclohexane. Like that. That is about the general characteristics, general introduction regarding the categorization of the molecule and their naming part and all. Try to work out as many examples as possible. For example, if you take this one, what is the UPSC name of the molecule? See, there is a functional group here, so you can start from here. 1, 2, 3, 4, 5. 1, 2, 3, 4. Even though there is 1, 2, 3, 4 at the presence of chlorine, you can take that one. You can take that one as the parent chain. No problem, you may take the other one also. It is possible to take the other one also. Since there is a chlorine, I am taking this one. So it is 1, 2, 3, 4. third one you have ethyl group, fourth one you have chloro, and second one you have isopropyl group. So what will be the name? What will be the name? 4-chloro, 4-chloro, 3-ethyl, 4-chloro, 3-ethyl, 2-isopropyl, 2-isopropyl, butane, 1-ol. That is the name. I repeat, 4-chloro, 4-chloro, 3-ethyl, 3-ethyl, 2-isopropyl, or you can use the systematic name of this unit as isopropyl. Will call the name 1-methyl-ethyl, 1-methyl-ethyl, which is same as isopropyl. So it may be 4-chloro, 3-ethyl, 2-1-methyl-ethyl, or simply isopropyl, butane, 1-ol, like that. Try to practice the naming part as far as the in-text questions, example questions. When you go to the last page of the chapter, exercise questions, all you must try to practice. What is the name of this molecule? It is 1, 2, 3. 3-bromo, 3-bromo, cyclopentane, 1-ol. 3-bromo, cyclopentanol, or pentan 1-ol, cyclopentan 1-ol, like that. This is an important segment regarding the structural feature of alcohol, phenol, and ethers. Let's have a detailed talk on this. When you take alcohol, for example, methanol compared with the phenol and the alkane, you see carbon, oxygen, hydrogen bond angle 108.9 degree, while here it is almost same, 109 degree. 108.9 means 109 degree. So bond angle, carbon, oxygen, hydrogen bond angle remain almost same whether you are dealing with the methanol or phenol. But here the bond angle is slightly greater. Quite naturally, here we have two bulky CH3 group. Here it is one hydrogen, one CH3, one hydrogen, one benzene, one hydrogen. So one side it is hydrogen, while there two bulky groups. Naturally, the bond angle will slightly expand. So here it is 109, 109. Here it is slightly greater, more than 110. It is close to 112. It is coming. What about carbon oxygen bond? Carbon oxygen bond length is 142 picometer, while here it is 136. That's quite interesting, while here it is very close to that. So carbon oxygen bond length, these two cases are very close, 142, 141, but here it is 136. Bond length decreases. Why carbon oxygen bond length less in case of phenol? All of you know, as the connectivity made is to benzene ring, and here we have a lone pair of electron. It will undergo resonance. There is a partial double bond character between carbon and oxygen, so the bond length will decrease. Moreover, this carbon is sp2 carbon, this is sp3 carbon. So sp2 carbon is more electronegative, will pull the electron density towards it, so the bond length decreases. So bond length in phenol, carbon oxygen bond length in phenol is lesser by how much? By 4 or 5 units, isn't it? By 4 or 5 units, it is lesser compared to alcohol and ether. In alcohol and ether, it is almost the same, 141, 142. While bond angle same in alcohol and phenol, while it is greater in ethers. So this must be the very important comparison regarding the structural details of alcohol, phenol, and ethers. Very, very important. Very, very important. This is sp3 carbon. This is sp2 carbon. These two are sp3 carbon again. That's a very important point. Now on to preparation of alcohols. Now preparation of alkenes. In fact, preparation of alcohol from alkenes. Right? There are a couple of methods, as all of you may be remembering. First one, acid catalyzed hydration of alkenes. Acid catalyzed hydration of alkenes. If you take ethene, ethene treated with water in presence of acid medium, you can see the hydrogen added here and OH added here. You get a CH2 turn, CH3, double bond becomes single bond, and you get CH2 OH. You get ethanol. Ethene converted to ethanol. Ethene converted to ethanol. Acid catalyzed hydration process, right? And if you take a propene unsymmetrical alkene, the product will be according to Markovnikov addition. Suppose we are taking propene. Suppose we take propene added with water in acid medium. Where does this OH minus go? The negative part of addendum predominantly connected to carbon containing less number of hydrogen atom according to Markovnikov addition, and the major product will be CH3, CHOH, CH3. You get N-propyl alcohol and isopropyl alcohol, and isopropyl alcohol will be the major product. 2 propan 2 all will be major product according to Markovnikov addition. Now, how this reaction happens, the mechanism we need to understand. We need to learn the mechanism, and in fact, it is dealt in detail in the classes. Let's see how the mechanism can be understood. The acid catalyzed hydration of alkene. The mechanism of acid catalyzed hydration of alkenes. As explained, this is the reaction CH2 double bond CH2 with H2O. With H2O in acid medium, you get CH3 CH2OH. How that reaction takes place? You see this HOH water getting protonated, and in acid medium it is available as hydronium ion. It is available as hydronium ion, right? Now the step 1 reaction, ethene is getting protonated. Ethene is getting protonated, and the result will be you get CH3 CH2 CH3 CH2 plus H2O, that is protonation of alkene. First step reaction, protonation of alkene. This loosely held pi electron attack hydrogen of hydronium ion, and you get water separated. This is first step reaction. It is called protonation, and you get a carbocation. You get a carbocation. In fact, it is maintaining carbocation mechanism. So wherever you take molecules where there is a chance of rearrangement of carbocation, it will undergo rigorous rearrangement and you may get some unexpected product, right? Now, the second step is attack of the nucleophile. The carbocation attacked by the nucleophile. What is the nucleophile here? Nothing, water molecule. Carbocation attacked by the nucleophile, and the net result is you get the so-called protonated alcohol. You get a protonated alcohol, right? And now the last step, deprotonation procedure. Deprotonation process. This undergo deprotonation. This molecule attacked by water molecule. You see, this O will attack this proton, and this electron transferred to oxygen. You will get CH3 CH2OH plus H3O plus. So step 1, protonation. In fact, this is the acid medium where you have hydronium ion. Step 1, protonation. Step 2, nucleophilic attack. This is nucleophilic attack. Who is attacking? Water molecule is attacking as nucleophile to get a protonated alcohol. And step 3, deprotonation. This H plus is removed. Deprotonation. That is the reaction involved acid catalyzed hydration of alkenes. If you are dealing with the unsymmetrical alkene, the reaction product will be according to Markovnikov's rule. And if you are dealing with the molecules where there is a chance of getting rearrangement possibilities, you will get a suitable different product. For example, you can try yourself what will be the product obtained. How many different products you can get? How many different products you can get if you are dealing with such a molecule given to you, taken for acid catalyzed hydration? You can try yourself. How many different products you can get by the hydration of this given molecule? And what will be the major product? You can try yourself, which is a very simple and a common question from the concerned area. I repeat, the question are how many product you get, how many alcohol you get, number 1, number 2, which is the major product. You try yourself. Okay, yes. So that is about preparation of alcohol from alkene. That is a carbocation mechanism. Next one, it is hydroboration reaction. It is hydroboration reaction. Hydroboration oxidation reaction. Hydroboration oxidation reaction. Next one. Hydroboration oxidation or hydroboration peroxidation reaction. The reaction involves, say for example, we take propene. We take propene and alkene, which is treated with the diborane, which is treated with the B2H6 diborane, followed by treating with the H2O2 in alkaline medium. You get, look at the importance of this reaction. You get CH3, CH2, CH2OH. You get the propan 1-ol as the major product. And that indeed is the importance of this reaction. Hydroboration oxidation, introduced by H.C. Brown, received a Nobel laureate because of the importance of that reaction, along with some other cases. So here, unlike the normal acid catalyzed hydration, where we get a secondary alcohol or similar other product, a primary alcohol directly obtained. One alkene give one alcohol. One alkene give one alkanol. That is the importance of hydroboration reaction. Propene gives propan 1-ol, normal propyl alcohol. Unlike the other cases, this is the importance of the reaction. The product obtained is somewhat look like the way it happened like in anti-Markovnikov addition. So remember, there is no connectivity with anti-Markovnikov addition. It has no connection with anti-Markovnikov addition. The product seems to be like that. The product obtained seems to be like what we get in anti-Markovnikov addition. Right? Let's see why. Let's see why this is happening. See, when you look at the reaction which is happening, propene is interacting with the diborane. How propene interacting with the diborane? That is the interesting point. CH3CH2 is interacting with the diborane. It is in fact interacting with the boron hydride BH3. It is interacting with the BH3, and thereby you get a transition intermediate. You get a transition intermediate like this. Boron is bonded here, and one of the hydrogen from boron is bonded to this carbon. The double bond, one pi bond is about to break, and this bond is about to form, and this boron hydrogen bond is about to break, and this carbon hydrogen bond is about to form, and you have BH3. You see that? BH3 How BH3 looks like? This is BH3. This boron about to make a bond with this carbon. So this bond is about to form. And one of the boron hydrogen bond starts breaking. And a carbon hydrogen bond starts forming. Meanwhile, carbon-carbon double bond is about to break. And ultimately, these two bonds will form and these two bonds will break. The net result is going to be, as you can understand, CH3, CH2, CH2, BH2. Hope you get the picture. So this boron makes a connectivity with this carbon and this hydrogen connected to this carbon. So CH3, CH2, CH2, BH2. Now the same thing happens with another molecule of propene. One more molecule is added similar to this. One more molecule is added similar to this. How is that? How is that? CH3, CH double bond CH2. With this carbon, boron makes a bond, and with this hydrogen, this carbon, this hydrogen makes a bond, right? And ultimately, what you are going to get is CH3, CH2, CH2, 2 times BH. This is monoalkyl borane, and now this is dialkyl borane. Each time you can notice the hydrogen is added to the unsaturation. Each time the hydrogen is added to the unsaturation. This is monopropyl, propyl borane. This is dipropyl borane. And it can happen 3 times. 3 times propene molecule getting added to boron. And the final result will be, final addition result will be like this, trialkyl borane. You will get trialkyl borane, R3B, like this. For example, in this instance, it will be CH3, CH2, CH3, CH2, CH2, 3 times B. In fact, structurally you can understand boron with 1 propyl, 2 propyl, 3 propyl. This is what the molecule. Tripropyl borane. Carbon 1, 2, 3. Propyl. 1, 2, 3. Propyl. 1, 2, 3. Tripropyl borane. Trialkyl borane. Hope you get the picture. Now, this is treated for reaction with peroxidation. H2O2 in alkaline medium. It is going to break over here. It is going to break here. It will break over here. It will break over here. It will break over here. And all the places OH group will be added. You can see 3 OH minus will be added to this system, and again 3 OH minus will be added to this part. What is the net result? You're going to get CH3, 3 molecules of CH3, CH2, CH2OH, and BOH 3 times. BOH 3 times, I don't have to tell you, this is H3BO3, boric acid. You get boric acid. And you get 3 molecules of normal propyl alcohol. This is what happening in hydroboration reaction where primary alcohol dominates. And the product seems to be like what we are getting in anti-Markovnikov type of product. Is it clear? Boron hydride added across the double bond, and boron connected to the terminal carbon, hydrogen connected to the interior carbon. And that is the reason why this is so happening. Hope the picture is clear. So number 1, acid catalyzed hydration. Number 2, hydroboration reaction. There is a reaction which is very important, but actually it's not in the syllabus, but sometimes it may be encountered in some of the examinations. It is nothing but, say, propene, CH3, CH, double bond CH2 is treated with mercuric acetate Hg2AC, mercuric acetate followed by NaBH4, sodium borohydride in alkali medium. It is called oxymercuration, demercuration. Oxymercuration, demercuration. It is not in the syllabus, but many times the questions may be encountered, and you can see the product obtained is similar to Markovnikov rule. Again, there will be an addition reaction, and the final product is Markovnikov product, Markovnikov type product. OH group comes normal type of the product. Markovnikov type of product is obtained, but remember, it is not a carbocation mechanism. Remember, it is not a carbocation mechanism. Remember, there is no carbocation rearrangement possibilities. It is a covalent reaction. It is a covalent reaction, and there is no chance of getting carbocation mechanism. There is no chance of predicting carbocation rearrangement, or so what we explain in acid catalyzed reaction we don't get here. That is a very important point. So these are the three important hydration procedure happening with the alkenes. Number 1, acid catalyzed hydration. Number 2, hydroboration oxidation. Number 3, oxymercuration, demercuration. That in fact is out of the syllabus content. Okay. Now on to the next. Next is from carbonyl compounds. Carbonyl compounds. Reduction of aldehydes and ketones. That is an important reaction coming next. From carbonyl compounds. Reduction of aldehydes and ketones. Reduction of aldehydes and ketones. How it is reduced? Catalytic hydrogenation. It may be catalytic hydrogenation. Hydrogen with platinum, palladium, nickel, etc. Catalytic hydrogenation. Finely divided metal catalyst with the hydrogen. Or it may be chemical reduction. It may be chemical reduction, sodium borohydride or lithium aluminum hydride. Aldehydes will be reduced to primary alcohol, and ketones will be reduced to secondary alcohol. Aldehydes will be reduced to primary alcohol, and ketones will be reduced to secondary alcohol. Say for example, we take ethanol. If we are taking ethanol, CH3CHO, ethanol treated for reduction. Either it may be hydrogen with the platinum, palladium or nickel, or it may be sodium borohydride, or it may be lithium aluminum hydride, like that. There will be a reduction. What is the procedure happening in reduction? CH3, CW. Here the hydrogen is added. In fact, the hydrogen is added over that CO double bond. You get like this. There is already one hydrogen, and there is oxygen like this. Oxygen is divalent. Here the reduction happens across carbon and oxygen. The reduction happens. H2 is added over here. So one hydrogen will be added to carbon and one hydrogen will be added to oxygen, and the result is CH3 CH2OH. You get a primary alcohol like that. What if it is a ketone? Suppose you are dealing with a ketone, CH3COCH3. Similar fashion, similar way. What do you get? CH3COCH3. The double bond is gone. What left with carbon, a tetravalent species, and oxygen, a divalent species? As it is explained, H2 is added across here. One hydrogen will be added to carbon and one hydrogen will be added to oxygen. That is the reduction. And what is the net result? You are getting CH3 CHOH CH3. You get a secondary alcohol. So aldehydes will give you primary alcohol, ketones will give you secondary alcohol. Reduction either by using catalytic reduction or by using chemical reduction. Is that clear? Fine. Next it is reduction of carboxylic acids and esters. Reduction of carboxylic acids and esters. Reduction of carboxylic acids and esters. Carboxylic acids reduced to primary alcohol either by using lithium aluminum hydride, or it may be better reduced by diborane. It may be better reduced by diborane to primary alcohol, and it gives excellent yield. It gives excellent yield, but many times we don't commit to this reaction because the lithium aluminum hydride is an expensive reagent. So we don't use that unless it is a special situation. Rather commercially what we can do is a carboxylic acid is converted to ester. A carboxylic acid is converted to ester, and an ester by using catalytic hydrogenation, it can be converted to alcohols. An ester using catalytic hydrogenation can be converted to alcohol. For example, suppose we are dealing with a carboxylic acid, say propanoic acid. Suppose we are dealing with CH3, CH2, COOH. What we do is, this is treated with say for example methanol in acid medium. There will be esterification reaction. You will get CH3, CH2, COOCH3. We convert propanoic acid to methyl propanoate, and now it is reduced by using catalytic reduction, hydrogen with the platinum, palladium or nickel. It is going to reduce over this region, CH3, CH2, CH2OH, like that. CH3, CH2, CH2OH, carbon 1, 2, 3, propanol, and one carbon alcohol, methanol, CH3OH, like this. So that is a commercial way, which is a pretty rather cheapest method, converting a carboxylic acid to alcohol by converting first into esters. Okay. Next, so catalytic hydration, acid catalyzed hydration, number 1. Hydroboration oxidation, number 2. Oxymercuration, demercuration, number 3. Reduction of aldehydes, reduction of ketones, reduction of acids, reduction of esters. Okay. Next, from Grignard reagent. From Grignard reagent, we can produce alcohols. Grignard reagents added with the carbonyl compounds. Grignard reagent added with the carbonyl compounds, you can get alcohols. How to get alcohols? Grignard reagent versus carbonyl compounds. Carbonyl compounds versus Grignard reagent. That's a very important context. Preparation of alcohols. You see the reaction. This is a carbonyl compound, maybe aldehyde or ketone, interacting with the RMgX. It is going to break here plus and minus, while this is polarizing as minus and plus. Agreed? Now R minus is connected here, O minus interacts over here. There is a addition product obtained. You get C R O M G X. You get such a addition product. Agreed? And now it is treated for hydrolysis. Now this is hydrolyzed. This part of the molecule will be hydrolyzed. It's going to break here, plus and minus, and H plus will be connected here to get alcohol. You get CrOH. You get alcohol. This is what the reaction. So Grignard reagent added across the CO carbonyl system, you get a addition intermediate, which upon hydrolysis we get the alcohol. Now comes the important point of discussion. Suppose we are taking formaldehyde, HCHO. Suppose we are taking methanol. Means I am taking methanol. Means here there will be 2 hydrogen. Means finally here there will be like this. That is RCH2OH. You will get a primary alcohol. So when you take methanol, the product obtained is primary alcohol. Very simple to understand. Suppose it is any higher aldehyde. Suppose I am taking ethanol. Suppose I am taking ethanol, CH3CHO, or any higher aldehyde. Just imagine. For example, CH3CHO, any higher aldehyde. The result will be R CH3CCHOH. That is a secondary alcohol. You get a secondary alcohol. So formaldehyde, you get a primary alcohol. Carbonyl compounds added with the Grignard reagent. If you take formaldehyde, you get a primary alcohol. Any other aldehyde, you get a secondary alcohol. If it is a ketone, you get a tertiary alcohol. If you take a ketone, you're going to get a tertiary alcohol. How to get a tertiary alcohol? Ketone will be like this, CH3CO. Ketone will be like this. You get COH, tertiary alcohol. So methanol, the final result is primary alcohol. Any higher aldehyde, the final result is secondary alcohol. And the ketone, the final result will be tertiary alcohol. This is an important point of discussion with the Grignard reagent. And in fact, Grignard reagent reactions, there are a lot of reactions to be studied. Apart from this, this is 3 important reactions from the syllabus content. You have to talk about Grignard reagent reacting with epoxy compounds, epoxides, substituted epoxides, how it reacts with HCN, how it reacts with RCN, how it reacts with esters, how it reacts with esters of formic acid, how it reacts with esters of bigger acids, bigger esters, how it is reacting with the methyl acetate. So reaction of Grignard reagent, methanol, higher aldehyde, ketone, epoxides, substituted epoxides, HCN, RCN, esters, ester of formic acid, ester of higher acids. The observation is different. So all these things, in fact, it is to be dealt in the course of study. And one by one. Anyway, all these will be discussed subsequently in the classes. Right? Anyway, that is the method of preparation of alcohol. Remember, for methanol, will give primary alcohol. Any higher aldehyde, you get a secondary alcohol, and a ketone, you get a tertiary alcohol. And that is about the preparation of alcohols. What are the preparation methods? Number 1, acid catalyzed hydration of alkene. Number 2, hydroboration oxidation. Number 3, additionally we discussed oxymercuration, demercuration, reduction of aldehydes, ketones, acids, esters, and reaction with the Grignard reagent. Right? And now it is preparation of phenols.